In the last video, we introduced the law of conservation of energy, one of the most important laws in all of physics. In this video, we will apply the law of conservation of energy to several examples. Let's start with a simple case relating work and energy. Consider this puzzle. A 50-kilogram probe is motionless in space. It turns on its thrusters. The thrusters provide 40 newtons of force and push the probe forward 10 meters before turning off. What is the final velocity of the probe?
In this question, we were told that we had a space probe that has a mass of 50 kilograms, and its thrusters turn on, providing a force of 40 newtons. Sometime later, we take a second photo of the space probe, find that it has moved forward, and the thrusters then turn off. Now, initially, the space probe was not moving. V equals 0. I'm going to place my origin at the thrusters of the space probe in their initial location. The x-axis will point rightwards, and we were told that the thruster travels an overall distance of 10 meters. So that's all the information we've been given. We've been asked to find what is the velocity of this rocket after it has moved those 10 meters. So let's go ahead and find that out. It would be possible to solve it using force and then kinematics, but let's see if energy can't get us to the answer faster. So, conservation of energy tells us that the kinetic energy at photo 1, I should actually specifically label these as photo 1 and photo 2, plus potential energy at photo 1, plus any work that was performed that pushed the rocket between photo 1 and photo 2, minus any work that went out, any energy that the rocket lost, so for example to friction, is all equal to the kinetic energy at point 2 plus the potential energy at point 2. Now, this might look like a bit of an onerous equation, but let's start looking at some of these more closely. Initially, the rocket was not moving. Kinetic energy is the energy of motion. So if a rocket is not moving, it has no kinetic energy. More specifically, when the velocity is 0, that means the rocket has no kinetic energy. Anything that has a velocity of 0 has no kinetic energy. Ke1 is 0. Pe1. We have seen two different types of potential energy. One is spring potential energy, and the other is gravitational potential energy. There are no springs anywhere in this picture, so we don't need to bother with spring potential energy. There's also no gravitational potential energy because this probe is not on Earth, it's not anywhere near any planet. There is no gravitational pull anywhere nearby. So Pe1 is out of the picture. Work in. Now we do have work in. It's being supplied by these thrusters over here. So that means that we do have to consider that. These thrusters are applying a force, and they're the thing that causes the rocket to get pushed over a distance. So there is work in. The thrusters are doing the work. Work out. Does the rocket or the probe lose energy, for example, due to friction? The answer is no. So there's no work out that we need to bother with. Kinetic energy too. Well, the rocket is definitely moving at the end. We don't know what its velocity is, but it is moving. So there is kinetic energy too. Potential energy too. Again, no springs in this question, and the rocket isn't anywhere near any sources of gravitation, so we can ignore potential energy too, for the same reason that we ignored Pe1. So, when you actually look through it, 4 of the terms in conservation of energy have cancelled out. They are 0. And so conservation of energy reduces down to the amount of work done by the thrusters is equal to the kinetic energy of the rocket after the picture was taken. So it's only this term, work in, and this term, kinetic energy 2, which play any bearing at all in this entire story. Now this looks a lot less daunting, doesn't it? Let's plug in what we know and let's solve. Work in is equal to a force multiplied by a displacement multiplied by the cosine of the angle between them. Kinetic energy is equal to 1/2 times the mass of the rocket multiplied by the velocity squared. Now, let's plug in all the information that we know. We know that the thrusters offer a force of 40 newtons. The displacement of the rocket was 10 meters. Now, the force pushes the rocket rightward, and the displacement of the rocket was also rightward. So that means that the force vector and the displacement vector line up exactly. The difference between these two vectors, the angle between these two vectors, in other words, is 0. Whenever two vectors exactly line up, the angle between them is 0. Is equal to 1/2 times mass of the rocket, 50. Velocity of the rocket, unknown. Now, let's simplify this somewhat. What is the cos of 0 degrees? It's 1. So now, this entire left side becomes 40 times 10 times 1 is equal to 1/2 times 50 times v squared. 40 times 10 times 1 is 400 is equal to 1/2 times 50 is 25 v squared. Now, 400 divided by 25, that's going to give us 16. And I should correctly put this down as being v2 over this whole place, since we're looking at the velocity specifically in the second photo. And finally, we take the square root of both sides. We get the size of v2 is equal to 4 meters per second. Or if you wanted to be particularly rigorous about it and you wanted to say the direction of v2 as well, since v2 is of course a vector, you would say that the direction of v2 is I hat. It's moving in the x direction. So we could say 4 I hat meters per second. And either one of these would be the solution. This tells you how fast the rocket is going after the thrusters have pushed it by 10 meters. Now you might be wondering what's the advantage of doing it this way. Among other things, if we had wanted to solve this using force and then kinematics, we would first have had to use force to solve for acceleration, and then use kinematics to use acceleration to solve for the velocity. This basically allows us to do it all in one step, thanks to the relationships of energy that we can take advantage of.
A common question we saw in kinematics was one where an object fell from a height. We will now show that we would get the same answer with energy. A 3 kilogram ball is initially at rest. It is dropped from an unknown height. Its velocity just before it hits the ground is 7 meters per second. What was the original height of the ball?
In this case, we have a ball which is initially elevated and it falls to the ground. We're going to look at its motion, and we're going to set photo 2 to be a nanosecond before it hits the ground. Initially, the ball is not moving. I'm going to set my origin at the ground. I'm going to set upwards as my positive direction. And at this point, we are ready to solve for the initial height of the ball. We could solve this using forces and then kinematics. So because we know what the force is that the ball is experiencing, we can work out what the acceleration will be, and we can work out what the final velocity of this ball would be using kinematics. In fact, you don't even need the forces step. You could just assume that this is going to be 9.81, that's the acceleration. But in this case, we're going to see if we can get the same answer using work and energy. So let's try it out. The kinetic energy at point 1 plus the potential energy at point 1 plus any work that comes in, work that is performed on the ball, forces aside from gravity or spring force that apply on the ball, minus any work out, work that the ball does, energy that it loses because of friction, for example, is all equal to kinetic energy 2 plus potential energy 2. So, kinetic energy 1. Initially, the ball is not moving. Kinetic energy is the energy of motion. So if the ball's not moving, there's no kinetic energy. More specifically, if the velocity is 0, that means that the kinetic energy will also work out to be 0, because kinetic energy is half times mass times velocity squared, but 0 squared is 0. But the ball definitely initially has potential energy, so we need to keep that term. Now, aside from gravity, there are no other forces acting on the ball, so work in must be equal to 0, as must work out. The ball is not losing any energy due to friction. All of that's going to be equal to kinetic energy 2, so the kinetic energy of the ball just as it strikes the ground, or a nanosecond before it strikes the ground. It is definitely moving at this point, so, and in fact we were told that the size of this velocity was 7 meters per second. So there is definitely a kinetic energy 2 over here. Potential energy 2. Well, now the ball is on the ground, so it has no height, so the potential energy is 0. It's not in an elevated position, so there's no potential energy. And of course there were no springs anywhere in this question, so it cannot gain potential energy that way either. So, what started off as conservation of energy has now condensed itself down to just PE1 equals KE2. So, PE1, mass times gravity times height, is equal to KE2, that's 1/2 mass times velocity 2 squared. We were told that the mass of this ball was 3 kilograms. So, mass 3, G, 9.81. We always treat 9.81 as positive whenever we're solving a work energy balance. Height, initially unknown, is equal to 1/2 times mass 3. Velocity, we know that it has a velocity of 7 meters per second, or more correctly, negative 7 meters per second, but when we square it, that negative sign is going to go away. So, so that means that this is just going to get solved out without having that negative sign there. Now, 3 times 9.81, that's going to give us 29.43 times h1 is equal to 7 squared is 49 times 1.5. So, half times 3 times negative 7 squared gives us 73.5. And now we can solve for h1 by dividing both sides by 29.43. The initial height is equal to 2.5, roughly. So that means that this ball started from an elevation of 2.5 meters. Now, just to be rigorous, let's confirm this answer using kinematics. So if we were to approach this using kinematics, and just for the sake of clarity, I'm going to do this out in a different color. We would say that the initial velocity of the ball is 0. The final velocity of the ball is 7 just as it hits the ground, so -7. And because I called this the x-axis for some reason, this is going to be 7 I hat. The acceleration upwards is positive, so downwards would be negative, our familiar negative 9.81. Yes, this 9.81 would indeed be negative, because this is an acceleration that we're talking about. In in the questions that we have, whenever you do work and energy, we treat 9.81 as positive. But in kinematics, remember, we can treat 9.81 as negative. The time is unknown, and the displacement is also unknown. So given all of this information, let us solve for what the displacement should be. We're looking for displacement. We know initial velocity, final velocity, acceleration. So there's only one equation that weaves together all 4 of those quantities, and that is toolbox equation number 4. So that says V final squared minus V initial squared is equal to 2 times acceleration times delta x. V final, -7, minus V initial, 0, is equal to 2 times -9.81 times delta x. So -7 squared minus 0 squared, that's going to give us 49 minus 0, which is 0. So 49 is equal to 2 times -9.81 will give you -19.62. So we end up with delta x is equal to 49 divided by -19.62, which is -2.5. Exactly the same answer. So when we're talking about a height, we can usually be a little bit more loosey-goosey than we would be when we're talking about a displacement. Displacement is a vector, and you have to be extremely cautious about what sign and what direction you're using. Height is generally assumed to be positive unless you're told otherwise. So in this case, we were told 2.5 meters, but because so much else in work and energy is a scalar, we can treat the height as also being a scalar, and we can just leave it as 2.5 meters, rather than as rigorously writing -2.5 I hat meters.
Let's not forget that there are 2 types of potential energy. Let's explore spring potential energy. A 4-kilogram object is placed on a horizontal spring. The spring is compressed by 0.2 meters and then released. The object reaches a velocity of 6 meters per second. It experiences no friction at any point. What was the spring constant of the spring?
In this question, we see an object which is on a compressed spring. This works a little bit like a pinball, which is being pushed by a plunger. But for our purposes, this square object might be a little bit easier to visualize. The mass of the object is 4 kilograms, and the compression of the spring was 0.2 meters, 20 centimeters. Initially, this object was pulled backwards on it, and photo 1 is going to correspond to the fact that it was pulled backwards. But when we release the spring, the object is going to start moving. This is photo 2. Now, we do not know what the spring constant is. But we were told that this object was moving at 6 meters per second. I'm going to set my x-axis to be at the back end of the object as it's on the compressed spring, and I'm going to set rightwards as being positive. Now you understand the way that I've drawn this, this spring is not in a physically different location than what it is in this place over here. It's just that I've elongated it. Now that we have all of this information, we are ready to apply conservation of energy. Kinetic energy 1 plus potential energy 1 plus any work that came in minus any work that went out is equal to Ke2 plus Pe2. So, initially this object is not moving. Ke1 is 0. This object is not at an elevated height, so there is no gravitational potential energy, but there is definitely spring potential energy. So Pe1 is not 0. Work in. There is no jetpack in this problem, so there's no force which is going to add energy to the block. Work in is 0. Work out. There is no friction in this problem, so we can ignore work out. Kinetic energy 2. The object is definitely moving at the end, so kinetic energy 2 has to be accounted for. Potential energy 2. The spring is now completely stretched out, or it's at its natural length. Whenever a spring is at its natural length, it has no more potential energy. And since this block has not changed its height at all, there's no potential energy from gravity either. So that means that Pe2 is also 0. So now, this entire equation simplifies down to the potential energy at point 1, which incidentally was due to the spring, is equal to kinetic energy at point 2. The potential energy at point 1 is going to be given by the spring potential energy, which is 1/2 times K times the compression of the spring, or the elongation of the spring, squared. And that's going to be equal to kinetic energy 2, which is 1/2 times mass times the velocity at point 2 squared. This one's actually pretty easy to solve. Let's plug in what we know. 1/2 times K is unknown, but the initial compression of the spring was 0.2 meters. And I won't even bother with the I hat or the J hat because this is going to get squared anyway. All of that's equal to 1/2 times the mass of the object, 4 kilograms, times the velocity of this object, which was 6 meters per second, rightwards. Again, since this is going to get, since the directions don't matter in energy problems and this is going to get squared anyway, I'm not going to bother with writing out the direction. So this works out to 1/2 times K times 0.2 squared is 0.04 is equal to 1/2 times 4 is 2 times 6 squared is 36. 1/2 of 0.04 gives us 0.02. K is equal to 2 times 36 is 72. So to solve for K, we just need to take 72 and divide it by 0.02. That gives us 3,600. And we have that K is equal to 3,600 newtons per meter. So that is the unknown spring constant of this spring. And we were easily able to solve for it using conservation of energy.
The potential energy at one point gets related to the potential energy at another. Consider this example. An object is placed on a vertical spring with a spring constant of 200 newtons per meter. The spring is compressed by 0.2 meters and then released. The object reaches a maximum height of 1 meter above its starting point. What is the mass of the object?
In this question, we have an object which is on a compressed spring. That was photo 1. But the compressed spring is then released, and the object is sent shooting upwards. Something like that. Now, so this over here would be photo 2. Photo 2 is taken at the peak of this object's motion. And at the peak, there is actually going to be no velocity, because at the peak of motion, there's never any velocity. The mass of this object is unknown, but we were told that the K of the spring is 200 newtons per meter. Now, the compression of the spring between photo 1 and photo 2, the initial compression of the spring, was 0.2 meters. And the final height of this block relative to where it started from was 1 meter. Now, we need to find out what the mass of this block is. The easiest way to do this is to set the origin at the initial height of the block. And we will see why that is easiest in just a second. First, let us set up conservation of energy. The kinetic energy at point 1 plus the potential energy at point 1 plus any energy that is gained through work minus any energy that's lost through work is equal to kinetic energy at point 2 plus potential energy at point 2. At photo 1, the object has not started moving yet. Kinetic energy 1 is 0. But there is potential energy 1, and this potential energy is coming purely from the spring. Why? Because we set our origin to be at the bottom surface of this object. If the origin is at the bottom surface, that means this object has no gravitational potential energy. So the only source of potential energy is from the spring. Work in. There's no jetpacks or applied forces or anything like that in this question. Work in is 0. Work out. There's no friction anywhere in this question. Work out is 0. Kinetic energy 2. This object is now at an elevated position, but it's more importantly at the peak of its motion, which means that its final velocity is 0. And if velocity is 0, kinetic energy is also 0. Potential energy 2. Since it's at an elevated position, this now has potential energy due to gravity. But there's no more potential energy due to the spring. Why? Because the spring has returned to its natural length. There is no more potential energy to be had in a spring that is at its natural length. So now this entire equation becomes the potential energy at point 1, which again was due to the spring, is equal to the potential energy at point 2, which was due to gravity. Potential energy at point 1 is 1/2 times K times the compression or elongation of the spring squared. And all of that's equal to the potential energy at point 2, which is mass, unknown, times gravity times the height at point 2. Now let's plug everything in. 1/2 times K is 200 times delta X, the compression of the spring was 0.2, squared. is equal to mass times gravity, 9.81, times a height of 1 meter. So, half times 200 times 0.2 squared gives us 4. Is all equal to 9.81 times mass. Easy enough. Divide both sides by 9.81 and you get a mass of 0.41 kilograms. So this was the unknown mass of the object.
We've seen a case where an object gains energy through the work done by an applied force. Now, let's look at a case where an object loses energy through the work done by friction. A 12 kilogram object is traveling horizontally at 6 meters per second. It enters a rough patch and slows down. It exits the rough patch at only 4 meters per second. What was the coefficient of kinetic friction?
In this question, we have a 12 kilogram object that passes through a rough patch. Initially, it's on a frictionless patch, but then it passes through a rough patch and it winds up on the other side. Initially, it's moving at 6 meters per second. So if we were to take photo 1 just before it enters the rough patch, we would see it moving at that velocity. Photo 2 will be taken just after it exits the rough patch, where it's moving at a velocity of only 4 meters per second. It has lost some amount of energy in this rough patch. The rough patch has a length of 5 meters. And that was all of the information that we were given. The thing that we were looking for was, what is the coefficient of kinetic friction between this block and the rough patch? Now that we have established what the question is asking for and what our information is and where our initial and final photos are, let us draw in our origin, which I will set at the left side of the rough patch, and our axis. I'm going to set positive x as being rightwards. In these types of questions, I don't really require you to draw a free body diagram unless there's a ramp involved, and then it's oftentimes easier to draw one out. But for the purposes of clarity, sorry about that. For the purposes of clarity, however, I am going to draw a free body diagram. It's going to have weight pointed down, the normal force pointed up, and if this were in the rough patch, there would be friction pointing left. Kinetic friction. Now, technically, you could solve for the kinetic friction and then mu sub k using first kinematics to find out what the acceleration of this block is, and then forces to relate that to the kinetic friction and ultimately the coefficient of kinetic friction. But let's see if we can have a shortcut. Let's see if energy will provide us with a shortcut. So, the kinetic energy in photo 1 plus the potential energy in photo 1 plus any work that comes in, any work that causes an increase in energy, minus any work that causes a decrease in energy as energy flows out of this object, is equal to Ke2 plus Pe2. The initial kinetic energy is definitely a factor here, because this object had velocity. It is moving at the beginning. So Ke1 is something we have to account for. Potential energy 1. This object remains on the ground this whole time, so its height is 0. So the potential energy 1 is not relevant. It's going to be 0 the whole time. Work in. There is no source of energy. There's nothing to increase the energy of this 12 kilogram block as it moves through the rough patch. So it does not account for either. Work in really only applies if you have a jetpack or rocket thrusters or something like that to increase the energy. But there is definitely work out. It comes from friction, the classic example of work out. So the amount of energy of this object is going to decrease as it passes through the rough patch. That's your tip-off that there is work out. Kinetic energy 2. The object is moving after it passes through the rough patch, so kinetic energy 2 is a factor in this equation. Potential energy 2. There is no change in the height of this object. It stays on the ground the whole time. So the height is 0, so the potential energy is also 0. So now this entire equation simplifies down to Ke1 minus the work out is equal to Ke2. So let's expand this out. Kinetic energy 1 is half times mass times the velocity at point 1 squared minus the work out is given by the size of the force that caused you to lose energy. In this case, that's the friction force, multiplied by the distance or the displacement of the object as it traveled through the rough patch, or as it traveled through the region where that force that sapped your energy was operating, multiplied by the cosine of the angle between the displacement and the applied force, or the force that caused you to lose energy. All of that is going to be equal to the kinetic energy at point 2. Now, let's plug in everything that we know. Half times a mass, 12, times the initial velocity, 6, squared, minus the force of friction is unknown. But the displacement of this object as it traveled through the rough patch was 5 meters, times the cosine of the angle between them. So this object felt a friction force which is pointed leftwards, but it traveled rightwards. When the force and the displacement vectors are in exactly opposite directions, we say that the angle is 180 degrees. And let's not lose sight of the fact that we had an absolute value sign around work out. We'll see why that's important later on. And all of that is equal to 1/2 times the mass, which was again 12, times the velocity at the end, squared. Now, let's start calculating what we can. 1/2 times the mass times the initial velocity, squared, gives us 216 joules of kinetic energy. Minus the force of kinetic friction is unknown, but the displacement was 5, and the cosine of 180 is -1. So we now have the absolute value of 5 times -1 is -5 times whatever the size of the force of kinetic friction is. All of which is equal to 1/2 times 12, the mass, times 4, that's the final velocity, squared, which gives us 96. Okay, let us simplify this still further. taking the absolute value of negative 5 times the sine of fk is going to give us positive 5fk. So this whole thing simplifies down to 216 plus 5 times the force of kinetic friction, or however big that was, is equal to 96. Or actually, no. Because I took the absolute value here, but there's a negative sign out front, that'll actually be 216 minus 5fk gives us 96. So, if I were to take 96 and subtract 216, I would get negative 120. So that now gives me that negative 5 multiplied by the force of kinetic friction is equal to negative 120. Divide both sides by negative 5. You get 24. So the force of kinetic friction was equal to 24 newtons. We're almost there. The force of kinetic friction is equal to the coefficient of kinetic friction, which is as yet unknown, multiplied by the size of the normal force. Now I'm going to solve this out in a little bit of shorthand. We know that the weight force was equal to mass times gravity, which will work out to mass 12 times gravity 9.81. That's 117.72. Now, this object is not collapsing into the surface, nor is it levitating from the surface. So clearly the total force in the y direction is 0. And for that to occur, the size of the normal force must be exactly balancing out the size of the weight force. So this is a pattern that we have seen over and over again in forces. Whenever an object is not moving in some direction, that means that all of the forces balance out in that direction. And the normal force is 117.72. So we now have that the friction force of 24 is equal to mu sub k, as yet unknown, multiplied by the normal force 117.72. So, last step. Take the friction force of 24 and divide it by 117.2, and that gives us mu sub k is equal to 0.204.
There's an interesting relationship between certain forces and certain types of energy. Let's look through the examples from this video. In the probe example, the thrusters provide an applied force. We need to use work in this puzzle. The falling object felt a weight force. We didn't use work in this puzzle. The object accelerated by the spring felt the spring force, obviously enough. Again, we didn't use work in the solution. The vertical spring question was very similar. Finally, the object that felt kinetic friction was solved using work. This is an interesting dichotomy. When weight and spring force play a major role in the puzzle, we don't use the work term of conservation of energy. But when applied force and friction play a major role, we do. Weight and spring force are called conservative forces. They are closely linked with the potential energy terms in conservation of energy. By contrast, applied force and friction are called nonconservative forces. They are closely linked with the work terms in conservation of energy. There are major differences between conservative and non-conservative forces. Because non-conservative forces are associated with work, they always change the energy of an object when they act on it. Because conservative forces are associated with potential energy, not work, they cannot change the energy of an object that they act on. There's a third major difference between conservative forces, like weight, and non-conservative forces, like friction, and that is best illustrated by this marble machine. Every ball in this machine is identical, so they all feel the same gravitational force or weight, and they all enter the ramp at this point, so they are all going to fall through the same distance. Since the weight force and the distance are the same for all balls, the weight force does the same amount of work on each ball. More generally, we can say the amount of work done by weight or any other conservative force depends only on the starting point and the ending point of the object. But the situation is different for the friction force. The different paths through the maze have different lengths and different inclinations. The friction force will do less work on the short, steep paths and more work on the long, gentle paths. The amount of work done by friction or any other non-conservative force depends on the path the object takes. This distinction between conservative and non-conservative forces might just appear interesting for now, but it becomes central in advanced fields of physics like thermodynamics. So it's good to be aware of the distinction early on. In this video, we saw several examples of the law of conservation of energy. In the next video, we will explore more examples.